the overall Chrome architecture, and then let's dig down into the few pieces. So a lot of this, you guys may already be familiar with, but even if Zach has been, here for not that long, I think it's worth looking into the details. So the general idea is we have a browser process. We have renderer processes. I'm going to draw one, but we can have many. It can be one per tab, one per site. Well, we have different ones that lives within a sandbox. And we have a GPU process, which I'm going to put here. Which is partially sandbox too. Matters on Windows in particular, but on other platforms as well. The browser is responsible for the UI. The renderer is responsible for rendering a page, running JavaScript, doing layout and so on, and producing pixels for.
That's okay.
For the browser to display. The GPU process is sort of a slave of all of these, whose responsibility is to talk to the GPU, the actual GPU machine. So, pre-Aura, let's start with that. Before any of this Aura stuff, or even before any of this GPU stuff existed, let's talk about this just because the code is still there at the very least, and it impacts some of the infrastructure. So ignore the GPU process for now. The renderer, what it does, it produces a backing store for the browser. The browser talks directly to the system to say, put a picture on the screen. The renderer renders the web page using WebKit, puts it into a piece of shell memory that we call a transportdib. Sends it to the browser through IPC, and the browser takes it, puts it into a backing store, and blips it onto the window. In particular, two things we do in here is we try to do partial rendering. If you just have a blinking cursor, we want to only redraw that cursor. We're going to have a transportdib that's the size of the cursor, and we're going to bleed it into the backing store that represents the
Mm-hmm. And on the browser side, we have a bunch of backing store cache.
Right.
So you can switch quickly between tabs.
Right. We don't keep a backing store for all the tabs. We discard them. We keep a cache of them. We want a backing store so that we can very quickly repaint the window, so that when you get damage, you get exposure or whatever, we get an event in the browser. We don't want to round trip to the renderer to produce these pixels. We just want to bleed it. That's why we keep a backing store in the browser. So that's the general architecture, and it's fairly simple compared to where we're going next, involving another GPU. So we added GPU acceleration in the renderer for several reasons. One is the idea of we can increase performance for at least some workloads, if not all of them. Two, certain features require a GPU. WebGL is one, if we want it to be reasonably fast, and so on. And we can establish the list of those, but it doesn't really matter. What matters is, from the renderer's point of view, as soon as some components of the page are rendered by the GPU, we essentially have to render the entire thing on the GPU. The reason being that getting bits back from the GPU is slow. Not only it's slow, it's also synchronous, it's overall very difficult to make it run well. So basically we decided that in the renderer, we're going to start rendering everything using the GPU. When I say rendering everything using the GPU, it mostly means the final picture that's produced by the renderer, instead of going into a transportdib, transportdib instead of transportdib, it goes into a GPU resource. So that being said, because the renderer is sandboxed, you cannot directly talk to the GPU. So that's why we introduced this GPU process, which has a sandbox, but it's weaker in that the renderer cannot access the GPU. The GPU process can, and depending on the platform, it can be restricted to a lower number of things. We didn't want to put the GPU stuff inside the browser for stability reasons. We've had, improved, over time, we've had so many driver issues, GPU issues, and so on. We didn't want to compromise the browser stability for GPU stuff. So,
is that gonna be true going forward? Because say we get a handle on stability issues, not being able to paint. I mean, if the GPU is jammed or GPU is hosed, there won't be much we can do.
There is no plan today to change this.
I guess what advantage do you see?
Well, it will reduce complexity. This was sort of, I mean, Windows went through this, right?
Mm-hmm.
They had the graphics stack in a different process, but then they decided at some point, look, if you're not gonna have visual output, then you might as well reboot.
Yeah, well, I guess a core tenet of the stability concern here has been that a lot of these stability problems have been infrequent. And so even though we temporarily no longer have a way to produce output, it's less traumatic to restart the GPU process and redisplay content than it is to kill the browser.
Okay.
That said, if stability problems disappeared, then I don't see any particular reason to keep the GPU process around, except that we might want different sandboxing policies on the browser, renderer, and GPU. And so we might still want all three of those to be different processes.
There's currently two things to it.
Is there a non-zero, is there a significant performance overhead to using the GPU process instead of?
Depends on the system. Sorry, you know more about
There's
this.
performance gains and loss. It moves the performance characteristics in different bits. It's not the fact of using a separate GPU process so far has not been a root cause of performance issues.
No, and in fact, Van Gels did an experiment a couple of years ago where he moved the GPU into the renderer to see if that helped, and actually hurt because we got, on desktop, we get nice parallelism between the GPU and the renderer. That is less true on low core.
Right. That's it. So for example, Android today runs the GPU process inside of the browser as a separate thread. So it still uses the same infrastructure, they're just saving them on the memory aspect of it.
On Windows, there is a performance impact, there's an extra blit that has to happen. And I think also on Mac.
Right.
It's an extra blit.
So where is that? Could you
So
elucidate?
we're going to get to that.
Right.
We're way ahead of ourselves there.
So whatever here, right now we certainly don't have a plan to remove this. I think we would have done a lot of things very differently if we had put the GPU directly in the browser. I think today, merging the processes wouldn't bring much to the table. They maybe save a bit. I don't think on those platforms in particular this is a performance issue. At least we haven't found that it is yet. Maybe it will. But in any case, yes. This for now is here to stay. And at least, even if we're going to merge, most likely the infrastructure to talk to this GPU process, which I'm going to go over, is probably here to stay as well. So, I guess going back to here, we decide we want to render the web contents with the GPU. What does that mean? as a first approximation, not too much. It just means that we're still going to use WebKit to draw pixels. We're still going to use Skia to generate pixels. We're just going to put them on the GPU. And then the few things that will use the GPU go directly to the GPU. So WebGL goes to the GPU, gets gets rendered into a texture, which is sort of the basic GPU resource as far as we are concerned here. And it gets composited with the rest of the page. So what does compositing mean? Well, the renderer looks at the page. He has lots of elements in the DOM, divs and images and iframes and canvases and so on. And compositing means putting them all together to produce an image, essentially. So we have to worry about things like overlap, like you have web content on the page, and then you have a WebGL image here. And then on top of it, so WebGL, on top of this here, so do this, you have, say, an image, right? Pretty picture. What this means is this guy here is going to go to the GPU. All of this, the text and so on, still rendered using the CPU, then uploaded to the GPU into textures as well. This guy here, we sort of would like it to be part of this, this page, but because it's on top of the WebGL thing, we actually have to layer these on top of each other. That is, when we draw things, we're going to draw the background first, then this, then that. Okay? Which means all of these have to go into different layers. And we have a compositor to take all of these layers and put them back into a single image that we can then send to the browser. So WebKit itself is the one that decides, hey, these various elements are going to go into different layers once we start accelerated compositing. So that's what we call accelerated compositing, which is an unfortunate term, compositing, because of the software compositor. But anyway, when you see accelerated compositing in the code base, that's what this means. It means we're taking the web page, we take all the elements, we distribute them into various layers, and we have something that takes the layers, put them together.
And these layers are logical blink layers. They're not CC layers yet.
Right. There's different levels of layer trees. There's, I believe, 2 in WebKit, then 1 in what we call CC, 2 in CC. I can go over this as well. Maybe I'll leave it for later. Let's ignore this for now. So,
Yeah, it's on my list, don't worry.
WebKit layers. CC layers.
I think there's at least 4 different object trees in WebKit.
So I assume this is a WebKit layer, right? And does that just mean the order that it sends the layers to the GPU? Kind of.
So it's more of a retained mode in that WebKit, so in the old path, WebKit is responsible for drawing. So WebKit emits the drawing command saying, draw this, then draw that, then draw that. In compositing mode, it's more of a retained API where WebKit says, I have 3 layers. One is this, the second one is this, it's on top. That one is there, it's on top. And we can have hierarchies. For example, we may need to apply opacity to this combination of layers because of the way it's done.
While we are on a tangent, you mentioned about text. Is there any long-term plans for, and he's writing it down.
Text.
Do not plan to render text.
I'll start with the current architecture, how we get to that, and we can talk about more things in the future. So I put it there, meaning
Good.
right now it's not we don't do accelerated text rendering yet. So we have this. So it's a retained API. What it gives us, when I say us, it means CC, the Chrome Compositor, a set of layers, and it's our responsibility now to transform that into a picture. So the way we're going to do that is by having this subsystem. So in the renderer we have WebKit, and we have CC. CC's responsibility is to do that. Take all these layers, put them together, produce an image. So what it does is figure out this is sort of a software layer, like it's rendered using Skia. Skia produces software bits. We're going to take all those bits and put them into textures, because that's the primitive that GPU has.
Subtle point of clarification, Skia sometimes produces GL commands. In this case, it's only producing software bitmaps. But for Canvas 2D, it has an OpenGL backend, which we use there too. So like in crash stacks and stuff, you may see this. Not really relevant for the core flow, but like that's confusing.
Okay.
So by rendering to texture, you mean it can directly draw on the texture in the renderer itself, or it's a...
Yes, rather than having its output be sort of like a software bitmap in main memory, you can have it populate a texture on the GPU via a series of OpenGL commands.
Okay.
It's on the list, we will get to that.
For the benefit of Zach, there's no rendering on the renderer. It just means that their GL commands get put in the command buffer, right?
So I was going to get to that.
Okay, go for it.
Yes, there's going to be a lot of tangents all along the way. You see that. Okay, so what CC does is, for software layers, those types, is going to want to put them into textures. For two reasons. We don't want to create one giant texture that represents the entire page. The two reasons are these. One, well, there's GPU limits. On the GPU, we cannot guarantee any arbitrary size. You go to the Wikipedia cat page, it's like giant, super long. It wouldn't fit into a single GPU texture. Two, it allows us to do, well, okay, backing up once. We could render the entire page, what's visible, and put that into a texture. That would pretty much in all cases fit into a GPU texture. At the end of the day, the GPU is capable of displaying this, so it has enough memory, enough limits are big enough that you could put this in. We don't want to have to redraw everything when we scroll. We cannot scroll textures themselves, so what we want to do is, instead of mapping visible pixels to logical texels, texture elements, we map based on what's visible, we map it based on the logical coordinates of the page. That is, if the page is like this and continues there, and you may have scrolled it, we're going to align the texture to the page itself. What this allows us to do is, once we've drawn the page, it's on the GPU, and we scroll, we just send different coordinates when we're going to draw those textures. So, to get to that point, so we want to map what's on the page directly to the GPU, but if the page is giant, we cannot map the entire thing on the GPU, so we're going to divide the page into tiles. So we create those essentially square things that cover the page. And they're small, 256 by 256 typically, or 512 by 512 on high DPI machines. I'm not sure exactly how we tune it precisely, it doesn't matter. What matters is we upload, at least in priority, what's visible, and then as we scroll, provided we have prepared, those tiles, it's just a matter of drawing these at a different offset on the GPU. So that's for software layers. For layers like WebGL, it's already a hardware layer in that what produces it does it on the GPU. So the GPU is going to redirect any GL command that is used to produce this texture to a texture. And so we have textures for these, we have texture for that. We can create more. We can create more for like videos and plugins and so on. At the end of the day, we have a bunch of textures. We have a bunch of coordinates. We can do a little bit of curling algorithm of saying, oh, when I made my tiles, one of those tiles is completely hidden behind this WebGL element, so we're just going to skip that tile. Or possibly cut it into pieces. If it's like this, we're going to say, hey, we only want to draw this part and so on. So we do a little bit of CPU work to reduce our workload, and then we're going to send all these to the GPU as drawing commands. Yes?
Do we use tiles even if we know that the total size of the page is really small enough to fit like on one texture?
Yeah, we do. We have a heuristic. For example, if it's thin and long, we're not going to cut it like typically for...
Yeah, so it's on a,
so it doesn't always use squares.
Layer.
It doesn't always use squares.
It's on a per layer basis, this heuristic that he's talking about.
Yeah.
So if you have just a page that is a whole one layer, nothing fancy, that's always big enough to end up tiled. I think it needs to be smaller than the tile size in one dimension.
It needs to be smaller in one dimension, but we allow it to be bigger. Basically, I guess the two constraints are the tiling is uniform per layer. That is, we're not going to try to make like one big tile and like two small tiles and do things like that. And then any dimension needs to be smaller than the maximum size allowed by the GPU, which can depend per GPU. And then there's a little bit more heuristics to say, we don't want to waste tiling when it really doesn't bring us anything. So,
but in practice, almost all layers end up being tiled, all web content layers.
I mean, the reason I ask is it seems like you could, obviously vertical scrolling is far more common than horizontal scrolling, so it seems like sometimes you could, most pages don't have horizontal scrolling at all, so it seems like you could just have one tile per row rather than
like
a bunch of horizontal, like strips, yeah.
We have experimented with tile shapes and sizes. Skia is better at drawing the long strips, which makes that attractive for that reason too, but
to some extent. I think if it's too long, then you get you get out of the cache.
These tuning things we've played around with, and we've never found anything that's universally better.
The input sucks.
Like prior
It's not
to the
controllable.
compositing kicking in the renderer, the old style used to be that painting used to be a synchronous operation, that the bitmap would get composed, sent to the browser, and then it would get printed on the screen. With the compositing kicking in, is that all happening in the same renderer thread, or is it
So previously it was not exactly synchronous. What used to happen is the renderer sends...
No, by synchronous I mean that the renderer thread is in charge of producing an image, and then it would send it in the transport dib, and then the browser would paint it.
Okay.
But with compositing kicking in, is that also happening in the main thread, or do you have another thread?
That's a good question. So in what I'm describing right now,
There's always a but.
because
this is the evolution.
It's the evolution.
You guys are asking about the next step.
So in the current version, yes, it happens on the main thread. The reason being that to be able to draw anything, we have to talk to WebKit, and WebKit you can only talk to WebKit on the main thread. So basically, Skia has to paint, at least has to get all the drawing commands from WebKit on the main thread. And so we'll get to the next evolution, which is impulse side painting, where we look at distributing that onto other threads.
It might be worth trying to explain the threaded compositor as a halfway step though.
Is it
Yes.
there? Is it enabled?
It's enabled on Windows, yeah.
It's not enabled on Linux. Yeah. So
It's not enabled on Linux. Sorry.
so well, maybe let's finish with like trying to see end to end and see the evolution from there.
Yeah.
Yeah,
So
let's do that.
CC now knows how to create all these textures and knows what commands it needs to send to the GPU to produce this. So now we get to this part of saying, CC has to talk to the GPU inside of process. How do we do that? So we have what's called the command buffers infrastructure. Basically, GL, which is I've mentioned this already, it's the low-level graphics API that we use and we standardize on to talk to the GPU. It's an API that's inherently asynchronous because GPUs like to be very asynchronous. That lets us manage this in a way that we can serialize the GPU commands, the GL commands, into a command buffer. So a command buffer is just basically a ring buffer where we're going to add commands saying, use this texture using this GPU program, draw quads or triangles or whatever, and go to the next. At the end of the day, present that. So we serialize those commands with their parameters into a ring buffer. So we write to it from this end, the GPU reads from it on this end, and gets all the commands, parses them, translates them directly into GL. They really correspond one-to-one very closely. Does some amount of security verification that we're not trying to do like something really crazy, and sends that to the GPU. The presenting part. So at the end of the day, the GPU created a frame buffer with, all this page, everything we wanted to do. How we put it on the screen is where things diverge between all the platforms. Let's start with maybe the simplest one, which I think is Linux and XP. On Linux and XP, the GPU directly accesses it. The GPU process directly accesses an H-wind or an X window, and so we just call the generic function called swap buffers that gives it to the OS to say present it. So at the end here we're going to say swap buffer. The GPU looks at this and says, all right, swap buffer is done, and then we call back to the renderer so that the renderer can tell the browser, hey, I'm done with the frame, you can give me more events, you can do whatever else you need. On Mac, the way it works is, instead of rendering to a visible frame buffer, we render to what's called an I/O surface. So an I/O surface is sort of this special type of texture that the GPU accesses. And then we share that with the browser. The browser then takes the I/O surface and blitz it into the, the view hierarchy, the NS view hierarchy, however that works, using OpenGL. So there's an extra sort of round trip from the GPU to the browser that says, hey, I'm done with this frame, go present it. The browser gets it, presents it, returns to the GPU so that it can continue its work.
So then the GPU tells the renderer, and the renderer tells the browser that it's actually done? Is that
Yes,
round trip?
right. So the renderer adds all these commands, tell what we call flush to the GPU, says, execute all the commands up to this point, because there, so I guess it's, one, the GPU process talks to the GPU, does everything. 2, sends to the browser blitz. 3, returns. 4, it goes back to the renderer and says, I'm done. And then, whatever other synchronization.
Which is like, yeah, I know, I just page flipped.
Well, you're kidding, but many of the bugs we've had
Yes,
were
more.
So
from this.
Can this
at
step
step 5, like
Hmm?
until step 5 happens, what kind of events are blocked in the browser?
Input events. So the browser regularly sends input events to the renderer, but you don't want to send too many because that would be bad. It wants to send only a certain number per frame, and it's going to block, so I can push back to the OS saying, hey, stop gathering the events. The reason is for, like, say, mouse moves. For example, on Windows, as if the mouse moves very fast, Windows will give you a mouse move event as long as you ask it for, right? Until the mouse doesn't move anymore. We never want to send too many input events to the renderer, because if the renderer takes a certain amount of time to process this event, you definitely don't want to be on the browser side saying, oh, grab events, and send them all to the renderer. The renderer is like, one event, oh, I have to do all this work, and then next one, oh, I have to do all this work. You end up increasing latency very badly without any way to know, hey, I should just drop this one because it's just a mouse event, and that's more common. So we have this pushback thing where basically we say, for every event we send from the browser to the renderer, we wait for a NAC before sending more. This 5, which is what we call update rect, it's a message, also does some things. For example, plugins and resize Axe and these sort of things. We'll go into the details of that if we want, but basically there are some things that the renderer cannot do. For example, in PAPI plugins, it just essentially H-wins that the plugin owns, that the browser is responsible for putting on top of the page somewhere. But it's not something that we can use in the GPU. It's not something that can tell the GPU, hey, use that as a texture and composite it. So basically what we do is, and that was true in the software case as well, is when we send this message here, we say, oh, by the way, all these plugin windows are now at that position, if you scroll and stuff. Which also means that with accelerated compositing, and PAPI plugins may be out of sync with the scrolling. You may see, you scroll the page and you see the page scrolling, the plugin catching up, and so on, like this. So the reason is that it gets swapped through here, but plugins get updated through here. Okay. So there was Mac. Windows is very similar in that, from the point of view of the GPU process, the GPU will, and correct me if I say something wrong, the GPU will render to an off-screen surface as well, and share that with the browser. The only difference is that here, instead of this happening on the UI thread on Mac, it happens on a different thread on Windows.
Why does it use a different thread?
So they're called present threads. I'm actually multiple of them. There are 4 maximum. The reason is because you don't want to present on the UI thread on Windows, because the present will wait until the vsync, and that can basically hang the window if you do that on the UI thread.
Okay, so it will block up to 16 milliseconds.
If you're at 60 Hz, yeah.
If you have variable rate.
Depends on your display.
You can change
Anywhere between like 50 and
by changing the settings of the display.
Right, the display drives the frequency
Yeah.
at which we can effectively swap. Yeah, we can talk about horrible things like
But if we
four-way deadlocks here,
but
which is one of the reasons this has to happen on another thread.
But if we present using another thread, and we couldn't be like sending more frames that Windows will discard the frames that.
What do you mean, sorry?
It means if you send frames faster than the refresh rate, isn't that a waste?
Oh, I
Is
see.
that what
Well,
you're saying?
there's feedback, so the renderer basically produces frames at the correct rate.
This we will block. So basically, we have back pressure here.
The thread that is presenting is the one that will send the ACK. Okay.
And so you have back pressure here, which falls back into back pressure here.
Mm-hmm.
So the renderer here says, okay, I'm going to send frames, and I'm going to allow up to 2 frames in flight. like the one I just did and the one I'm doing now. But after 2 frames, it's gonna start blocking, saying, hey, yeah, I haven't heard back from the GPU process, so I'm just gonna stop.
So the browser process on Windows uses DirectX to do the presenting, right?
Correct.
Is that the hard boundary between DirectX and Open? Is that the only place DirectX is used? Is in the browser process?
It's used, but the browser process and also the GPU process, we implement OpenGL on top of directory.
Surprise!
We implement OpenGL in terms of directory.
Yeah.
That's
What
right.
does that even mean?
So,
Angle. It's called angle.
Okay.
Yeah,
Crazy code.
basically just it maintains all the GL states and it transforms GL commands into the equivalent directory.
Okay.
GL drivers are shitty on Windows is the main reason.
So
Right. Yeah, that's why.
And they're not
Yeah.
installed.
The GPU
I
process.
think it's actually the reason.
Yeah.
They're
The
not
deployment's
installed.
not very high. Or installed, I
The
guess.
GPU process always tells the browser to present, or does it also?
On Windows Vista
Vista and
Plus,
later, unless we
yes.
blacklisted the texture sharing that we need
So the browser is the one who's actually doing the directory calls to.
to
Yes.
present to the window, yes.
So there's three.
Because you're in the sandbox and you cannot do that.
But then we have directory inside GPU process too.
Right.
Right, but because of the sandbox, the H-wind doesn't actually, it's not accessible. So in XP we present directly to the window because the sandbox doesn't let you do that.
It's a weaker sandbox,
It's
isn't
a
it?
weaker sandbox, but on Vista and later we tighten the sandbox in such a way that the H-wind isn't available. So we decided to have a shared texture which can be mapped into both the GPU process for writing and the browser process for reading and presenting to the screen.
So how does hardware video decoding work? Like, where does that happen?